Welcome to the fourth lecture video for Physics 10. We wrap up our study of kinematics in this lecture. We return to looking at kinematics mostly conceptually and descriptively, sometimes with some help of computer simulations. As we look at the three examples of motion covered in textbook sections 1.7, 1.8, and 1.9. The first section gives an overview of these examples, focusing on the definitions of free fall and projectile motion, and how the key assumption / approximation of the definition simplifies the considerations by treating air resistance as being negligible. The next two sections cover projectile motion. We first look at different aspects of projectile motion with the help of PhET simulation to help confirm and develop our intuition. And another borrowed lecture section from Physics 4a is used to illustrate and explain a puzzling scenario of why a ball launched from a launcher on a cart lands back on the same launcher even when the cart accelerates down an inclined track. Finally, the last section looks at the circular motion covered in section 1.9, centripetal acceleration, noting that this type of motion will feature again later in the semester. This lecture wraps up our 2-week study of kinematics. Next week's lectures start on dynamics, which looks into the causes of motion. Okay, so we are starting lecture 4. In lecture 3, the last lecture, we looked at some mathematics of motion under constant acceleration. And that was the most mathematical part of what we are covering in kinematics. And it's probably going to be the most mathematical part of the entire semester. So in this lecture, I just want you to look at 3 specific examples of motion, some of which happen under constant acceleration and some that don't. I have this infographic generated by Notebook LM. I've been using it, and I think this is actually a good way to use AI. Again, I'm looking for your feedback on if any of this is helpful. I will point out any mistakes I see in the infographic as I go over it. So I'll talk about free fall first. That's our first example. And free fall is actually just an example, maybe the most common example of motion under constant acceleration. So there isn't something new here, but there are some vocabulary, definitional issues that I want to point out that I want to make sure people have a solid conceptual grounding in. And after talking about free fall, I'll show you the 2 examples of 2-dimensional motion that the textbook covers. In the textbook, so these are in sections 1.7, free fall, 1.8 covers projectile motion, and section 1.9 covers centripetal acceleration, which is associated with circular motion. So I'll talk about this after talking about free fall. In fact, the free fall is a special case of a projectile motion. So there's some connection there also. So let me first talk in some detail about free fall. Zoom in. I had a Notebook LM generate these infographics in portrait mode so that I can do this. Zoom into each section. And then I'll scroll down after I'm done talking about this. So it's probably good to start with the definition of free fall. What is free fall? It's what we describe a movement or an event happening where an object moves under the influence of gravity alone. The movement of an object where the only force, which we'll talk about in the next week, acting on it is gravity. This has certain implications. And I want to make sure I touch on 2 of those in the next couple of minutes. One is that through this definition, we are ruling out certain types of motion that you might have thought was free fall. One that we are excluding is the cases where air resistance is significant. Because if there's a significant air resistance, then the object is not moving under influence of gravity alone. And that kind of goes with this example here. I think in your homework, you have an example of an Apollo astronaut dropping objects on moon where there's no air. You can do the same experiment on Earth. You just have to make sure that the object that you're dropping is in vacuum, so that regardless of the characteristic of the object, whether it's a hammer where it takes a fair amount of movement for air resistance to become important, or whether it's a feather where you drop it anywhere, there's air resistance is going to start to have a role almost immediately. And when we refer to free fall, we are referring to somewhat artificial setup, especially if you're dealing with a feather, where we made air resistance irrelevant. Under that particular approximation, simplification, as the infographic here says, mass doesn't matter. So without, there's a typo there. Let me fix that. Without air resistance, a hammer and a feather fall at the exact same rate. That's a feature of free fall where only gravity acts. On Earth, the gravitational acceleration is 9.8 meter per second squared. That's the constant rate at which objects would be accelerating under free fall. And here's the second implication of this definition. The direction of a velocity doesn't matter. Sometimes people look at the fall part and think that means things are moving downward, and sometimes they are. But that's not the important part of the definition. The more important part is really the free part, where there's no other thing that's influencing motion of the object other than gravity. Let me use the second half of the graphic to talk about this. Free fall in motion. So imagine a ball being thrown up. At the highest height, it may be moving horizontally, but vertically, its vertical speed is 0. So if we are talking about ball thrown straight up, then at the top, velocity would be momentarily be 0. And the constant downward acceleration continues to pull it down, and then eventually the ball has downward velocity. And I'm not sure what this means. An object is unvected. Let me just cross this out. I think this entire thing is at best redundant. Even if I could correct what unvected 0 meant. And sometimes people think it's this part that describes free fall. And what I am saying is, according to the definition above, that free fall is when an object moves under influence of gravity alone, that even while the ball is moving upward, it is in free fall. So from this point to all the way to the top is also free fall. Or another way to put it is this entire motion. From the beginning to the end, as soon as the ball leaves your hand until when it's caught, the whole thing is free fall. And I think this will make sense once we start talking about forces, because things that are relevant physically stays the same whether the ball is moving up or down, especially if you can ignore air resistance, which we do for description of free fall. Oh, and there's one little part of this infographic that your textbook does mention in one of the examples about the symmetrical speed, that the object's speed only depends on the height. It does have connection to something that we'll cover in a few weeks as we talk about energy. So let me just highlight this for now, but we won't be using this much this week. But I want to highlight it as we'll come back to this idea when we start talking about energy. Okay, so that's a free fall and all the salient details of what's involved in free fall. Now, for projectile motion and circular motion, you have additional videos that will showcase some computer simulations you can use to make sense of those. So let me just speak briefly in this video. just to make sure that we don't miss anything. So the two examples of motion in two dimensions you will see in the textbook, chapter 1, and in the rest of this lecture video set are projectile motion. And the section is called centripetal acceleration, and it has to do with moving in circle. So let me first talk about projectile motion. So in projectile motion, as you look at this definition, a projectile is any object moving through the air under the sole influence of gravity. If that sounds like it's exactly the same as the definition for free fall, yeah, they are, and not by accident. This is same as free fall because free fall is an example of projectile motion. I guess the key difference is when we say projectile motion, we start paying attention to the two-dimensional aspects of the motion. So there would be a trajectory to think about what you see in this picture. This is a kind of an illustration of trajectory. Imagine there being a tracer for the projectile. What the tracer traces out, that's your trajectory. And in this class, conceptual physics, we're not going to go heavily into math. But if we were to, and there are some conceptual questions that we can ask that can be addressed conceptually. I think you see some of this in the simulation. As you think about projectile motion, one key thing, if you realize it, it'll help you think about projectile motion clearly, is what's called independence of vertical and horizontal motions. You have a lecture section coming up in which there's a demonstration of a ball being launched from a launcher on a cart. And the conceptual way to handle that is by recognizing that motion in two directions that are perpendicular to each other, or as some people might say, orthogonal, they are independent. Motion in one direction, say vertical direction, doesn't affect the horizontal motion. Motion in the other direction, horizontal portion, doesn't affect the vertical motion. That's especially the case with the approximation that we are making, that it's moving under sole influence of gravity alone, meaning no air resistance. And if we were handling projectile motion more quantitatively, we would be using what's highlighted here. We break down the motion into horizontal component and the vertical component, and work through the equations. But we are not going to do that. Any questions I ask you about projectile motion will be conceptual. And your textbook makes a brief mention of this, that orbital motion is a kind of a projectile motion. You can imagine a projectile being fired at greater and greater initial speed, and at some large range. The fact that the surface of Earth curves will be important. And at some point, you can imagine this ball curving downward toward the center of the Earth. Won't be curving enough that even though it's curving toward the center of the Earth, the ground curves away so that it remains at the same height relative to the ground. That's basically the orbital motion. Now, this speed is pretty fast. It's like several kilometers per second. And if you are achieving the speed while you are in the atmosphere, you will burn up from all the friction and the heat generated in the air resistance. So actual orbiting objects are out in space where it's vacuum, and you can maintain that high speed without worrying about air resistance. So there's a brief mention of that in the textbook. And finally, this is the kind of two-dimensional motion that I used to skip. And the first time I taught this class, I realized that you can't skip it because the circular motion, we're not going to handle it quantitatively, and to handle it quantitatively would involve a fair amount of math. That's why we are not going to handle it quantitatively. We still need to talk about the idea of acceleration that exists in a uniform circular motion, where car, for example, is moving in circle at a constant speed. It's still accelerating towards the center of the circle. This type of acceleration is something that we will see again as we go into introduction of quantum mechanics. And when we get to that point, I want to be able to refer to the idea that something that is moving in a circle is accelerating. And there are consequences of that acceleration when the object that is moving is an electrically charged object. So you will see the textbook cover centripetal acceleration, and I think there might be one or two homework questions that I ask at a conceptual level. And I don't know what an aid-ways force is. I think it's meant to be sideways force. It's what you feel is a sideways force when a car makes a sharp turn. Yeah. And I guess this last picture, this kind of combines both the circular motion and the projectile motion, the orbital motion, orbits, like circle can be a shape of orbit, and as you are undergoing that circular motion, there's a centripetal force, centripetal acceleration due to centripetal force due to gravity. And since it's still a motion under gravity alone, it is a kind of projectile motion. So this just combines everything. Again, we are only going to cover this conceptually, not quantitatively. So that's the three examples of motion that you will see in the rest of this lecture. Well, the rest of the lecture will actually cover this last two, the two-dimensional motion. This is all you will hear about the free fall. So in the rest of the lecture, you will see the projectile motion and circular motion examples, simulations to help you make sense of it. And let me know of any questions. Thank you. Hi. In this video, we will look at a couple important features of the projectile motion. Because mathematically working out the details of the projectile motion requires at least trigonometry level math, we are not going to do that. But there are some details we can look at without doing all that much math. This is especially possible thanks to PhET, PhET simulation available from University of Colorado. We will use the projectile motion simulation. First, let's use the intro tab to illustrate one important principle of projectile motion, independence of horizontal and vertical motion. You can see that if we launch our projectile with the initial speed of 0 meter per second, the projectile just drops straight down. I want you to pay attention to these dots, which indicate where the projectile was at a given time. The big dot marks the 1 second mark. If we launch the projectile with the initial speed of 5 meters per second, then this is what you see. And if we launch the projectile with initial speed of 10 meters per second, it lands farther. And if we launch at speed of 15 meters per second, it lands even farther. This part is fairly intuitive. Now, this is the part where I want you to pause for a bit and think about this question before I give you the answer. As we increase the initial launch velocity, how do you think that affected the landing time of the balls? 1 Mississippi, 2 Mississippi, 3 Mississippis. All right. Depending on your thinking process, you might have thought the time would have taken shorter because of faster speed, or maybe you thought the time would have taken longer, maybe thinking like a glider. What surprises many students at first is that all these 4 projectiles landed at the same time. You can see with these dots, at 1 second mark, they all dropped about halfway down of the initial height of 10 meters. And it took another 0.1, 0.2, 0.3, 0.4, 0.4 to 0.5 seconds to drop to the ground. Whatever horizontal motion they were undergoing was not relevant to the vertical component of the motion, and this is because the vertical motion is independent of the horizontal motion. Now, let's look at projectile motion for an object launched along a level ground. I think some aspects of this come intuitively to many students. For example, fixing the initial speed at 15 meters per second. If I asked you at what angle would you have to launch the projectile for maximum distance it'll travel, many would say 45 degrees. Oh, let me disable air resistance. And you're right. Now, let me try at a little less angle. And a little more. To see that the range is indeed maximized at 45 degrees. The 45-degree landing spot was slightly further than 40 or 50-degree landing spot. Now, here are some fun facts I can demonstrate. At any range you can reach with an angle other than 45 degrees, you can find two angles to reach that range with. See how far the projectile lands when I fire at 25 degrees. And if I fire the projectile at 65 degrees, it lands on the same spot, but it does spend a little more time in the air. Alright, this has been a fun simulation. Before I say goodbye, I can show one more thing, which is actually in your textbook. That is the analysis of the horizontal and vertical components of the motion. If I turn on these velocity vectors components, you can see how the vertical component changes, like that of a projectile thrown directly upward, and how the horizontal component doesn't change. And you can confirm this by looking at the acceleration vector. It points directly downward with no horizontal component. Please feel free to find the simulation on the PhET website and play with it on your own. Projectile motion is a very common physical phenomenon in everyday experience, and a good intuition for it is as practical as anything else you would learn in introductory physics. And we have an example of kind of things you can try out in the upcoming video clip. This was recorded in a past classes, a virtual class session. Please give it a watch. So, projectile motion. What's good about simulation is it's good to test, play with the stuff. I don't know. I guess without a particular prompt or particular thing that you're trying to do, it can be a little bit like playing Minecraft, which, wide open sandbox. Open is great. You can do open is great until all the range of choices are a little bit too much sometimes. Let's see, what can I do here? I think I can try out some scenarios. So I think here's one that's familiar with a lot of people, which is that, okay, at 0 meter. Wow, height of 0 meter looks weird. So this is, I think, a kind of prototypical scenario. On a level ground, at what angle should you fire this cannonball so that it reaches the maximum distance, maximum range. And I think most people have good enough intuition to say it should be 45 degrees. That's going to give you the maximum range. And I can test it out a little bit too. And, fire it at slightly higher angle, 50 degrees, and see that it lands, can't zoom in. See that it lands slightly before the 45 degree. And I can try launching it at 40 degrees and see that it again lands slightly before 45 degrees. In fact, at the same spot that 50 degree one did.
So I think that's good enough. And you can also test it at different speeds to make sure that this result isn't somehow dependent on your initial speed. Now, higher initial speed will mean that it goes farther. Can I scroll? Okay. Higher initial speed will mean it goes farther. Um, oh, maybe I can make it 20. Try to take up the whole screen. Okay, that seems better. So that's the 45 degree at 23 meters per second. And I can test it out again. 50 degrees, it falls a little bit shorter. Um, 40 degrees, it goes a little bit shorter again. So I think that's easy enough to answer for most people, just intuitively. Now, here's the kind of question that good to answer to see how good your intuition about uh, projectile motion is. And at the same time, because it's kind of difficult to work it out mathematically, even in a calculus-based physics class like Physics 4A, this would be one of the harder questions. That's where having a simulation helps, because simulation can help you just test out the answers without going through all the math yourself, because this is simulating the real world physics. So this is let me just post the two questions that are sometimes that asked often. And it's one of those questions that I think you can answer pretty quickly if you have good intuition. But if you're still developing your intuition, then it can be challenging to answer. So let me write the question down on the screen so that I have it written somewhere. Um, so question one would be, how does angle of max range change if ground is not level? Or in this particular case, the easiest thing to do is can I not? Raise the cannon up to a higher height. So that would be effectively making the ground not level. So that wherever the cannonball will end up landing is going to be at 0 meter height, but the cannonball starts at 50-meter height. So that's one. Will it still be 45-degree angle that gives us the maximum range, or will it be something else? Will it be less than 45 degree, or will it be more than 45 degree? So that's question one. And question two is a similar question, as in, how does angle of max range change if not ground, if it's not truly a projectile motion, as in if air resistance is significant. And this question would actually be too difficult to answer mathematically, even in Physics 4A, even for people who've taken Calculus 1 and did reasonably well. Because this involves differential equations, and I don't know if I can do it all that well. But what's nice about simulation is that with the simulation, they can do numerical calculation, and computers are super good at doing numerical calculation. And there's a way to turn on air resistance. And with the air resistance turned on, I can just try out stuff to see what the answers are. So um, so I guess let me try this. So I don't know, this virtual class session, it's not really it's not conducive to making it super um, interactive, especially with the recording on. So you're welcome to participate. If you're somehow in a place where you can't quite participate, that's fine. This is what I would ask you to do. Let's try tackling question 1. So I'm going to drag this up and put it at the height of uh, 10 meters. And this is the question I'm posing to everyone. And I would ask you to answer in the chat. You are welcome to send it to everyone, or you can just send it to me as private message if you don't want a recording of your presence here. So this is the question, the form of the answer I'd like you to give. So, as a multiple choice. So A, B, C, where A would be one where you said that angle of the max range is still gonna be at 45 degree. B is where angle of max range is less than 45 degree. And C, angle of max range is greater than 45 degree. So let me give people a few seconds to make a choice. Send the answer in the chat, A, B, or C, either to everyone or to me privately. And once I had some chance for some people to answer, I will I'll give it a try, see what we get. So I see a couple answers. I'll give you 10 more seconds before I start trying stuff. And this answer is really more for you than anything else, because I think until you answer it, you haven't quite thought about it. I see a lot of A's. I see some B's. No C's. Interesting. So let's give it a try. That's the wonderful thing of relation, that you can just try it and see see what you get. Okay, so I'm already out here. Let me try shooting something at 45 degree and see um, if it's gonna stay in screen. All right, it's staying in screen, good. Okay, so 45 degrees, so this sets down a marker. So this is the place to beat if any other angle is gonna be the maximum angle. So since I had some answers for B, so let's try B, 40 degrees. Ah, it went slightly over. So this becomes a search process then. Okay, so 40 degrees gave me something that's farther away than 45 degree. Let's see if 35 degree gives me something even farther. Okay. So at 35 degree, I'm actually at a similar place as a 45 degree. So it looks like at this height of 10 meters, somehow 40 degree is the angle that gives the maximum range. And the simulation is where you can kind of explore a number of things. So okay, so we have one answer here, that with all this set of parameters, that 40 degree was the one that gave the maximum range. Now you can ask the question, does this change if some of these parameters change? What if my initial speed is lower? I actually don't know the answer in this question. Let me give it a try. So with a 40 degree, I get that. With a 45 degree, it's worse, okay. Although it hit the target. Let me try 35 degree. Huh, it's actually farther away than the 40 degree was. Okay, so apparently once you are no longer on level ground, then, and 30 degree was probably close, 30 and 35 were close to each other, and 25 is around the same. Is it all gonna be the same? I actually don't know. Okay, at 20 degree now, it's definitely less than where all the other stuff were. So so you get the result. That I think between those two attempts, one consistent thing that you got was that whether it's at 45, whether at 40 degrees or whether it's at 30 degrees, that the angle that gave maximum range was less than 45 degrees. And I think let me kind of land this plane. This is where having some explanation for your intuition is useful, because I think it was helpful for me to think about it in this way, that when it was on level ground, so when you fire something at 25 degrees, didn't go too far. And at the same time, if you fire something at 70 degrees, it also didn't go very far, although it went really high. And you can kind of see between these two what they are lacking. When you fire something at very low angle, a lot of that velocity is in the horizontal direction. So that's great. But because it doesn't go very high, what you have as a limitation is that this cannonball doesn't stay in the air for that long. And when you fire something at a very large angle, it stays in the air for a long time. But the horizontal velocity is so small that it doesn't move that much horizontally. So you might think of 45 degree as the angle that strikes the balance between the two. That enough of the speed, the component of speed, the velocity, is in the vertical direction to keep the cannonball in air, while there's also enough going in the horizontal direction to keep it moving horizontally. And 45 degrees, the angle that struck the balance between the two when it's level ground with air resistance. And the natural, then the question you could ask as you imagine changing the situation is how changing the parameters. What if it's not level? Or what if air resistance is slowing things down? You can see, does the 45 degrees still strike that balance? And if not, which way will balances shift? So I think the fact that no one answered the C doesn't mean all of you have a fairly good intuition, because I think whether consciously or not, I think you saw that being positioned at a higher height does mean that being like firing at a higher angle doesn't really buy you much of what you need. And whereas being at a smaller angle gives you, kind of allows you to trade more of what you have, which is with a higher height, you get more time in air. So you can trade that additional time for more faster velocity horizontally. So I guess I'm out of time to do any air resistance stuff. So I guess I'm not doing that, but the point of me showing this simulation is so that you can play with it for yourself. Let me just get rid of my annotations here.
In this section, you are going to see videos that I'm borrowing from Physics 4A. The first part is a short demonstration of balls being launched from a launcher on a cart under a few different scenarios. I hope you watch them carefully, try to do the predictions yourself. And the second longer part of the video is the explanation. There's a conceptual part to the explanation that I thought would still be appropriate enough for our conceptual physics class, which is why I'm borrowing this set of videos from my calculus-based physics class. And now the second part of the explanation is the brute force method of just doing the calculation. It has content that goes beyond what we are supposed to cover in this conceptual physics. You will see some trig functions. And I just want you to say upfront, you don't have to worry about the second part. I'm including it in case it's interesting to some people, but if the conceptual part makes sense, great. That's all I wanted everyone in this class to get out of this particular section. I will repeat this note at the beginning of that brute force approach to explaining what you will see with this launcher on cart demo. Please give it a watch. So this is the cart and the launcher setup for demonstrating the independence of the horizontal and vertical motion. This is the ball, and this is the coin used to trigger the launch manually. And here's the cart and the launcher itself. So let's see how this works. After putting the ball in, first we are going to trigger the launch manually using the coin while the cart is at rest. And the ball goes back into the launcher. Now we are going to trigger the launch while the cart is moving using the little metal piece mounted on the pole. And the ball still goes back into the launcher. Let's try that one more time. There you go. This is explained by separating the motion into horizontal and vertical components. When the ball leaves the launcher, it has the same horizontal velocity as the launcher. And as it undergoes the vertical motion up and down under gravitational acceleration, it continues to move at the same speed horizontally, so it ends back at the launcher. Now, I want to make this interesting by putting the launcher on an inclined plane. Watch what happens when we launch a ball while the launcher is at rest. That's what you would expect. The ball lands outside of the launcher. Now, what do you think will happen if we let the cart roll down? I'd like you to pause for a bit here and make a prediction first. Would you have predicted that? Let's try this again. This time with a bit shallower angle so that the cart has more time to roll down. I want you to think through this again while I get the track ready. Once again, let's test this by manually launching the ball with the launcher at rest. And the ball lands outside the launcher again. Now, give it another prediction. Where do you think the ball will land? Did you expect that? Let's give it just one more try. We are going to release the cart closer to the trigger so that it moves slower. So that's the demonstration. The challenge is, can you work this out analytically? It's an interesting challenge. The first time I saw it, it wasn't easy to answer. I think it's worthwhile for me to kind of go through it and do the explanation that some people were looking for. So the scenario, just so people are aware of the context, is it's coming from this demo. And with some of the demo videos, I don't explain things in full detail. I just put this as a challenge question, answer for yourself. And people keep telling me, I want to know the answer. So I think I should do that. So let me do that. So I'm not gonna play the whole thing. I'll just skip to the part where I do the demo on the inclined plane. Yeah, this is the inclined plane, and just to make sure the things make sense, if I just wait, did I? Yeah, and if I simply launch it from here, then it doesn't, it does the thing you would expect. The ball falls out because the incline fires the ball at an angle, so it falls out. Let me just go to the very last part where it's demonstrating. So now when you let the cart accelerate downward, so you are not launching it, or I guess I do that there, and then after that I'm letting it, wait, I think I do it at least one more time.
So when you let the cart slide down and do the other thing, the ball lands back in. And when I first heard this claim, I actually thought that's not going to happen that way, but I did a demo and it happened that way. So since we know experimentally how it should happen, there must be a theoretical explanation. So let's try to do that theoretical explanation. Let me call this way. Explanation for launcher on a cart on an inclined plane or track. So I'm starting from the assumption that people have seen the demo on a level plane, level track, and if the cart has some initial velocity, then as this thing triggers the launch mechanism and the ball is launched, because the ball launches with the inherited velocity and the vertical and the horizontal motion are independent, the ball, when it comes back down, it lands back in the cart. People have seen the demo and that makes sense. Good. And when it's on an inclined plane, it's not often obvious to people that basically the exact same thing should happen. So here's one way that I would, in search for a simple explanation, here's one way you could maybe try to explain it. So imagine, so this is the track, and so you are going to have a cart moving on it with some, along the track speed as a function of time. And you are going to have a ball that is being launched, which is being launched with some initial speed that's perpendicular to the track. So if you are comparing with the exact vertical, then there's some slight bit of an angle there. And the vertical, as usual, is being defined by gravitational acceleration. Acceleration is in that direction, minus g. And when the train was perfectly level, we appealed to independence of the two perpendicular directions of motion. That vertical direction and horizontal direction, they are independent. That's why when the ball has vertical motion, doesn't matter, it still lands on the cart. So now when they are on an angle, the thing is, nothing stops you from appealing to that exact same reasoning. These two different directions of motion, this direction, let me call that x, and this perpendicular direction, let me call that y, they're still perpendicular to each other. They are, the motion along x and motion along y are still independent. The only thing that changes is, let me put it this way. So I think one way that allows you to kind of see this is, so you can take this and basically rotate it, rotate it, let's see, so that your track is in the horizontal looking thing. So I'm gonna rotate it so until, okay, my track looks horizontal. So, and my y direction that I drew before, it now looks vertical. This is like a change of reference frame kind of thing, perfectly valid mathematically. And once you've done that rotation, then what you're beginning to realize is, so the acceleration that was pointed straight down before, now it's tilted a little bit to the right. So it'll have component that's vertical, that's what's making the ball come down, and it'll have this tiny component that's to the right. That's what's making the cart accelerate. And here's the amazing thing. Moving under influence of gravity alone, these x and y components, well, the y component, it doesn't quite work on the cart because there's normal force supporting it, as we'll learn this week. But the x component, it's acting on the cart. And this same x component also acts on the cannonball, on the ball that's up in the air. So as far as their x component of motion goes, it's common to both the ball and the cart. And that's the only thing that matters to ensure that by the time the ball lands, the cart will be at the same position that the ball will be in. And again, because the y and the x direction of motion are independent of each other, and what makes them independent is really this 90-degree angle. because they are independent, the fact that the ball has this acceleration doesn't matter. It just makes it come back down, and by the time it comes down, they have the same x position. So that's one way to answer this question. Just to conceptually, quickly, you do a change of reference frame, and if this argument makes sense, great, you're done. No more work needed.
And I do mean that both for students in my calculus-based physics and in my conceptual physics. This conceptual explanation is correct and I think sufficient on its own. What follows next is the brute force method that does the same thing as the conceptual explanation, just with more work in longer amount of time. I'm leaving it in this lecture video set in case anyone's interested. If you are familiar with some trigonometry and mathematical expressions don't scare you, then feel free to watch it. Also, feel free to skip it. There isn't anything from the following brute force method that we are using anywhere else in the class.
But sometimes people aren't satisfied with that. You want more work. So you can also do this mathematically. So the way you would do it mathematically is you would have an expression for describing position of these things. And I guess let me just to make this more painful for me and use the straight axis. That way, I don't have to be concerned with any reference frame shenanigans. I'm just doing the horizontal as my x, vertical as my y. So what you can do is you can describe motion of the cart and the ball. So I think describing motion of the cart will be easier. So I'm gonna just use the straight axis and not do anything fancy. I'm just gonna use the brute force method. I'm going to express the position of the cart and the ball and just to work through the math. These conceptual tools, they are useful. They allow you to answer questions quickly, and that's really what physical intuition means. But it takes time process to develop that intuition. So that's why I'm going through the math right now. So for the cart, let's see. I know the magnitude of acceleration of the cart. I'm just going to use a formula that I happen to have memorized. You will learn how to derive this and next week. And this magnitude has to be broken into two parts. So if I imagine acceleration as being vector like this, it'll have this leg and it'll have this leg. So AY and AX. And this is still the same angle theta. So my AY will be this hypotenuse times sine theta. So it'll be G sine square theta. My X component will be G sine theta cosine theta. So this describes how the cart will be moving. And I think I can skip, because these are all both constant acceleration, I can skip to describing the position of the cart. Its x position will be 1/2 x acceleration, g sine theta cosine theta t squared. And I'm gonna the other two terms are both zero. Zero initial velocity, zero position. So I'll just leave them be. And the y position of the cart will be 1/2 g sine squared theta t squared. So these describe the cart. And with this, I have a mathematical tool to basically, at any given time, determine where the cart is. Let me do something similar for the ball. So for the ball, it's going to have initial velocity with the x and y components, and then it'll undergo projectile motion. So actually the acceleration of the ball, it will only have y component minus g, because that's how the ball should go. Projectile motion, and the x component will be zero. The thing that I have to take care is that, let me draw it here first. So this is going to be my initial velocity vector. It'll have a vertical component and a horizontal component. So, and once you track the angles through, then this should be same angle as the theta as the angle of the track. So the vertical component will be Vi cosine theta, and let me just call this V naught. And the horizontal component will be V naught sine theta. So with that, so my initial y component of velocity is V naught cosine theta. My initial component of initial x component of velocity is V naught sine theta. So with that, I think I have enough information to just write down the kinematics expression that expresses where the ball will be at some arbitrary time in the future. So that'll be position of the ball as the horizontal position of the ball as a function of time will be V naught sine theta t. Good. And its initial position is 0, and horizontally it doesn't accelerate. My y component, the vertical position of the ball as a function of time will be minus 1/2 gt squared, the acceleration part, plus the initial velocity, V naught cosine theta t, and initial y position is 0. So I have this set of equations, and to speak out loud like what I'm solving for. So at the time when the ball lands, that's the snapshot that I want to get at. The moment when the ball supposedly lands on the cart, they share the same x position and the same y position. Now, I don't want to assume the thing that I want to be proving. So let me just use this condition to say we are looking at when the y position of the cart will be equal to the y position of the ball. So that's going to be the starting place, and I'm going to be asking the question, will the x position of the cart be the same as the x position of the ball? If they are, then the ball will have successfully landed on the cart. So let me set up this equation first. I'm going to say the y position of the cart, 1/2 g sine squared theta, t squared, t is unknown right now. That's equal to the y position of the ball, minus 1/2 gt squared plus V naught cosine theta t. Okay, I'm sighing a sigh of relief, mainly because, I think I made a sign error. There should be minus sign here because the cart is moving downward. Let me put a minus sign here. I think I fixed the sign error. I'm still sighing a sigh of relief because every term has a factor of t, so I can cancel out a factor of t. And the remaining algebra I only have to solve for a linear. So I don't have to use any quadratic formula. That always makes things simpler. So I think I can just solve for t. Let me solve for t, and that'll be the tool that I need to figure out if this expression will be equal to this expression. So solving for t, in the interest of time, let me just do that in my head. Watch and see if there's any mistake. If there's mistake, let me know. So just doing it in my head, t is going to be equal to V naught cosine theta over 1/2 g, 1 minus sine squared theta. Oh, I can simplify this a little bit. So let me simplify. 1 minus sine squared theta is the cosine squared theta. So it's going to be V naught cosine theta. Let me move 2 over. I hate nested fractions. 2 times g cosine squared theta, and I can cancel out that one factor of cosine theta. So the time at which it lands will be t is equal to 2 V naught over g cosine theta. So let's just plug in this value of t into the expressions for the position, and see if they are equal. Maybe they are equal, maybe they are not. I mean, I'm inclined to think they will be equal because experiment shows they are. Let's plug it in and see. So the position of the cart at this moment in time is going to be 1/2 g sine theta cosine theta, and this thing squared, 2 v naught. Let me do the square and distribute them in so that I can cancel out some things. So 4 v naught squared divided by g squared cosine squared theta. Let me just do a bit of cancellations. One factor cancels out, one factor cancels out, and I can say that x of cart will be, and one factor cancels out, so it'll be 2 v naught squared sine theta over g. And I think all the units work out here. Yeah. So that's for the cart. Let's write out the position of the ball. That'll be v naught sine theta times this, 2 v naught over g cosine theta. Oh, wait. Made a mistake. There's this cosine there that I forgot to write out. Cosine theta. Okay. So with that, I think that's it. So I have 2 there. I have v naught squared, sine theta, g cosine theta. So this indeed is equal to the position of the cart. So this method took a little bit longer, but I guess the benefit of this approach is the kind of the brute force mathematical approach. It eliminates a lot of what ifs. Because sometimes as you are making conceptual argument, it is possible to make a mistake, make an argument that's not valid. And in the brute force method, it's easier to check if you've made an algebra error. And I think I fixed all the errors I've made. So with that, so this is another way to show that even with the inclined track, by the time the ball lands, then the cart will be at the right position to take the ball. And if you are trying to find the reason how did that work, one might be that because the cart has moved downward a little bit, the ball had more time to move to the right. So even though, I don't know, that's one way to look at it. I think in the end, this is a surprising scenario, and this is my explanation of it. 2 approaches. One conceptual way to get at it with change of the reference frame, just imagine rotating it, and the other approach where you just work out the math. And when you work out the math, it turns out, yes, what happens in reality is backed up by mathematics.
Hi! In this video, we'll look at accelerations involved in circular motion. The main reason we are introducing circular motion in this class is so that we can refer to this when we talk about rotation later in Unit 2. So I'll try to keep this brief. Because velocities and accelerations involved in 2-dimensional motion can be complicated to describe in words, I will use PHET simulation called motion in 2D to illustrate the velocity and acceleration vectors. If you want to try this out, you will need to download it and run the Java simulation. So this is the motion in 2D simulation. You can see that as I drag the ball around, 2 arrows appear. The green arrow is the velocity vector, and the blue arrow is the acceleration vector. See if the directions and lengths of these vectors make sense. Let me show what happens with linear acceleration 1 and linear acceleration 2. That seems reasonable. Okay, if this makes sense, then let's now see what the velocities and accelerations look like in circular motion. So this is what we call uniform circular motion. Uniform part refers to the constant speed. Observe how the length of the velocity vector does not change. Now, because the velocity vector is constantly changing direction, an object in uniform circular motion is accelerating. And when we say that, we are using the physics definition of acceleration, which is the rate of change of the velocity vector. Not the everyday definition of acceleration, which refers to speeding up, like in an acceleration pedal. Note how the acceleration vector points towards the center of the circle that the object in uniform circular motion traces. Because the acceleration vector is always perpendicular to the velocity vector, it does not lead to the length of the velocity vector changing, increase or decrease, but it does lead to the direction of velocity vector changing. Section 2.8 of your textbook is called centripetal acceleration in reference to this acceleration. Centripetal means center seeking, just as how this acceleration vector points towards the center of the circle about here. And for an object to display uniform circular motion, it must be undergoing a centripetal acceleration. It also works in converse. An object undergoing a centripetal acceleration will move in uniform circular motion, tracing out at least a portion of the circle. So that's all. When we get to rotation, we will talk about rate of rotation and other fun dynamical quantities. The next clip is from a past virtual class session where I demonstrated how to access this simulation and illustrated some of the things you can play with in the simulation.
So this is the PhET website. They've gone through some changes in the recent years. I guess it's kind of about HTML5 and all that stuff. And you can find the simulations under physics. So these are fairly usable. I think mostly intuitive. So if I check motion, looking for kinematics stuff, one of the simulations I'm looking for is just here. I think it's this one, projectile motion. So yeah, and these HTML5 simulations, they're great. They run practically on any device, any modern device, any cell phone or smartphone or a tablet, all the modern web browsers. So this is what I like to use. And I'll play with this for a bit, but I wanted to show one, I guess, trick in case there were some people looking for one of the simulations I was using. So there was a simulation I was using to illustrate centripetal acceleration. And if you are looking for it here, you will see that you don't see it here. And the um, reason for that is this filter. There's a filter for HTML5. I think starting this year, they had this filter on by default, because when you turn this filter off, you will see quite a few simulations. So some of them take a bit of an effort to run, like this. So anything with the F symbol, which are flash simulations, there is a way to run it, but you have to kind of go through hoops. And I think I'll describe that at some point. But so I think they didn't want to show this by default. So that's why to turn it off to kind of show all these. And the centripetal acceleration simulation, yeah, it was this one. It's a Java simulation, which means you need to have a special program installed, or there is a browser compatible version which does not run on iPad, but I think it'll run on PC, and probably Mac OS as well, as long as it's not iOS. So, but this is actually an improvement. Before, you used to have to actually install Java runtime environment to do this. So So yeah, so this is one of the this feels super slow, but um, anyways, so maybe I'll come back to this after a bit of playing with the projectile motion simulation. Um, but I wanted to show that in case, so in order to get access to this simulation, you have to kind of go through that trick of this turning off one of the filters, which is there by default for a good reason, because ones that are not HTML5, it takes a little bit of effort to get it to work. Sometimes it doesn't work. But as long as you are aware of those limitations, you can turn off that filter to see all the simulations that PhET has had for decades, and that's been great for many different things. With the circular motion, I really just want you to show one thing. The reason I want you to be able to access it is so that, well, you can access it and run it for yourself. What I want you to show you is, which I think I can at least talk through in the next minute or so, as it as soon as it loads up, is the circular motion. I think I do cover it in the lecture video, but you can play with it yourself here. So these two arrows that show, the green arrow is the velocity. You can see that it's pointing in the direction of the movement. And can I move it faster? No, it doesn't actually make it move faster. Um, all right. So that's the velocity. And the blue arrow that's showing, that's the acceleration. It's showing the acceleration. And with this motion, what you see is that in this, what's called uniform circular motion, that this is moving at a constant speed. The length of this arrow is not changing. But as it's moving in circle, it is accelerating because the velocity is changing, and the change of velocity is represented by this acceleration vector. And this is one of the kind of unintuitive application of the physics definition of acceleration, meaning rate of change of velocity, which could include the change of direction. And this is the, and we didn't need to talk about centripetal acceleration and circular motion in general, because later in the semester, you will see some significant examples of circular motion. And you need to know that the circular motion always involves acceleration in the physics sense. So, okay, I think that's all the time you have. Thank you to everyone who's here. Any questions people had that people wanted me to address? No questions, comments you want to leave in recording? If not, let me stop the recording here and say goodbye to people joining by recorded the video, and I'll stay online for a little bit in case there are any questions or people had a one-on-one things to handle. So, so bye to people joining by recorded the video.